First of all, miniDog version 1 and version 2 merchandise is now available. I have t-shirts, bags, mugs and stickers, and the link to my Teespring store is in the description below. I also have Patreon and YouTube channel membership if you'd like to support the channel. All these projects are open source and the link to my GitHub is also below. But yes, you read the title, it's time to build the ultimate robot dog. Moving on from openDog to openDog version 2, using all the R&D from my miniDogs that I built and also my test dogs that I built last year using brushless motors which can be back driven, and that was a really good way to get compliance. I'm going to show a lot of the design process in this build, but let's first recap where we got to with the R&D and we'll talk about what's going to happen and how I'm going to proceed with openDog version 2. The original openDog was rather heavy. It was pretty rock solid though and made from 6 and 4mm CNC aluminium plate as well as some steel tubing and 3D prints and of course nuts and bolts as well made of steel. I used large brushless motors and ball screws to drive all 12 axis. These are driven with openDog Robotics brushless motor drivers and 8192 CPR encoders, so with the approximate 2:1 belt reduction and then the ball screw reduction it should be pretty accurate and it's definitely really powerful. I calculated and coded an inverse kinematic model which was explained in parts 9 through 11 of that series, so check those out on my channel. This means that I can move the feet in XYZ Cartesian coordinates and the software works out what to do with the rest of the joints to get the leg and the foot to the demand position in those coordinates despite the complicated geometry. I also experimented with interpolation which cycles through all of the foot positions from start to destination so the foot can move in a direct straight line between 2 points over a specific period of time. openDog also has an inertial measurement unit which is a gyro and accelerometer that tells you which way up it is basically or how much it's tipping in degrees, so it can attempt to balance. Although the results are pretty mixed, it's really hard because it's so rigid, so if it's not perfectly balanced and one foot hits the ground too hard, then it pushes it the other way and that really impacts all the other moves and it can never recover. I did get it to walk statically stable at one point though, although it's quite clunky and not very dynamic looking because it has to shift its weight from side to side as it does so. I then went on to test out load cells and I did that in my Sonic the Hedgehog robot build in an attempt to see if we can make the ball screw driven robot more dynamic. It looked pretty okay and it responds a bit like it's quite springy even though it's rigid and there's no springs in it, but I didn't think it was really reactive enough to help us with openDog with such a powerful and rigid mechanism that really needs to respond quite quickly. This is mainly due to the latency in reading the load cell, conveying the data and processing it and then of course physically driving the motor in reaction to it. Somewhere along the way I did some experiments with some other test legs and dogs driven by brushless motors. Each leg has just one motor in it for testing, so we can test it impacting the ground basically, but it also has a very low gear reduction with just one belt reduction stage and one gear reduction stage, so that means it can be back driven really easily with any force as the foot hits the ground. I use the existing motor encoder to drive both the leg to the demand position and then also see where it is being back driven to. So then I used a PID controller on top of that to drive the new demand position part way to the actual position where it was, and depending on the gain and the parameters of that controller I can make the leg more or less compliant and react in different ways to the force. My motors are pretty underpowered though, they were pretty small diameter and fairly high kV, so I had to build a lighter version of the dog to test it properly with 4 legs that can actually hold its weight up. This dog used the inertial measurement unit again to try and balance, making the legs on one side or the other more or less compliant based on its angle of roll based on the inertial measurement unit data. The legs only just hold it up though due to the underpowered motors, but we can see an immediate difference from having stability turned off to turning it on. It carries on stepping almost indefinitely until the batteries go flat at least. Lots of its mass, including the batteries, is balanced on top, and I did that deliberately to see if it was actually working. It can't walk anywhere of course though because it's only got 4 motors and no other leg axes. So I just set the leg position so it's roughly balanced front to back. Next, I really wanted to see if I was actually capable of making a robot dog that can walk dynamically, taking more than one leg off the ground at a time and balancing on just 2 legs as it walks. This looks really easy when it's done well by dogs from MIT and Boston Dynamics, but it needs to be aware of its balancing point and keep its centre of gravity over the balancing point as it goes. I decided to build a smaller robot dog using RC servos, and given the success with my compliant test dogs that had back-drivable gearboxes, I also thought it would be a good idea to have some form of compliance built into the joints. I developed a spring mechanism with magnets and a Hall effect sensor that can easily be read by the analog in of an Arduino, and I use that to sense how far the spring is getting stretched and therefore how much force is being applied to the joint. So this showed some early success, although it's hard to say how much, and I built the whole dog and almost got it working well. Like openDog, it had an inverse kinematic model which was driven by interpolation, so the feet can move in straight lines in XYZ Cartesian coordinates. Most of its ability to walk on two legs at a time came from some simple hacks based on the IMU data. I varied the speed of interpolation that made it walk faster or slower, and also translation back to front so that its mass stayed over the balancing point, so I made it work a bit like a two-wheel balancing robot. There's quite a bit of mechanical slop in this design though, but it appeared to prove out the principles for dynamic walking. So then I thought it was worth a redesign to test a new version to solve some of the mechanical issues. I made an entirely new mechanical version, which is miniDog version 2, although the electronics were taken from the previous version, and this time I didn't bother to install the magnets and Hall effect sensors. This one walks really well with 2 feet off the ground at a time. The stabilisation's been simplified. I just fixed the rate of interpolation so that it walks at a fixed rate. Then I use the IMU data to make it translate backwards and forwards in reaction to the robot's pitch. However, I'm really pushing the maximum speed and power of the servos in this build, so it will require a decent chunk of cash to be spent to make it work any better or do anything much more complicated. So I was really happy with how this one turned out. Of course, it only weighs 5 kilograms and openDog is about 50 kilograms due to all the metal, so I've made this as light as I can with some aluminium tubes and mostly 3D prints. So there's hardly any inertia in it compared to something much bigger, so we're right on the edge of really needing that compliance which we need in a much bigger dog to try and keep it stable. So I zip tied all the springs out in the end, so there is some compliance in the joints, but hardly any, and there's a bit of backlash in the servo gears. So we're kind of on the edge of that working really, so anything bigger is going to need some compliance built in. I really like the way I did that with the brushless motors and the back-drivable gearboxes. So I think to get this to work we'd really need to smash the feet into the ground a lot faster, so we'd need some much faster, more expensive servos. That's quite a chunk of cash to upgrade all 12 of course, because we've got 3 motors in each leg and 4 legs. So that means the springs would actually stretch when it hits the ground, but they wouldn't stretch under normal conditions. At the moment they're either too tight to have any effect, or if I loosen then it's like walking on big springs that's really unpredictable, so that doesn't work well at all. So I really want to combine the back-drivable brushless motor-based mechanism with motors that are more powerful, because that system of stability seemed really easy to make work quickly. Then I can use more IMU data like I did with the miniDogs to add the extra dynamics for walking, and hopefully with more powerful motors and agile joints I'll be able to make something that works pretty well. And also I can actually get the feet to the positions I want, when I want, instead of them being quite laggy as they were in the miniDogs. So let's have a look at some of the brushless motors that I used in some of the previous builds, and also what we're going to use in the new build, which is slightly different. So this is the motor we used on openDog. There were 12 of them. This is a Turnigy 6374 149 kV motor. It's about 2 kilowatts at 48 volts. We're running it on 24, so we got about a quarter of that. It weighs nearly 900 grams, which is about 2 pounds in weight. So fairly hefty, 12 of those on there, so nearly 12 kilograms of motors. Plus everyone had aluminium pulleys and those ball screws, which probably weighed the same again, so we had quite a lot of that mass was just motors and ball screws. Next up is a really similar motor but much smaller. This is a 5055, it's 280 kV, and another Turnigy one, and these are the ones that we used on the back-drivable dog, so this one's considerably lighter. It's about 1500 watts, but obviously the diameter is quite a lot smaller there, so basically you don't get quite as much torque, and obviously the can length is smaller as well, so generally speaking it's quite underpowered. So this is the motor we're going to be going on with in openDog version 2. It's another Turnigy motor. It's a Multistar 9225. This one's 160 kV. There's also a 90 kV version. It weighs only 400 grams and even less with without the long cables that are provided. And this motor's rated about 1200 watts. But of course it's a much bigger diameter. The can here is 90 millimeters, so we should get much more torque out of this purely because of its diameter and the extra leverage angle that we get. So the plan is to use the highest torque, lightest motor we can with the lowest gear reduction so that we can make the robot move really fast and we can make it easily back-drivable, and then we can work on the compliance. And that's going to be crucial to getting a larger robot than something this size to work in anything like a dynamic fashion, or pretty much to walk at all. So there are various ways we could do the gear reduction. One of those is a planetary gearbox of course, or just spur gears, but there is even a 3D printable open source version available called openTorque, which is a planetary gearbox, and it even uses the same motors that I'm planning to use. You should check out the YouTube channel Scientific, who's built one of these recently, and you should also check out his channel for more robot arms and loads of really similar projects using brushless motors and O-drives. However, I really want to keep the weight down as low as possible. So I was looking at the MIT Cheetah robot, which uses planetary gearboxes for all the axes, but with a belt drive down to the knee. So its actual knee motor is in the shoulder, and that means the mass is all kept in the body rather than it being thrown around in the legs. And that means the legs can move really fast, and there's no problems with that extra inertia. So then I thought, why don't we just use a belt reduction for everything? As long as the belts don't skip, it should be fine. We can easily get perhaps a 5-to-1 reduction from the motor here to the actual pulley, and that'll be about the same size with a 20mm pulley on there and a big pulley, and we could do that for every axis of the robot, and that'll make it easily back driven, and it also means it's going to be quite agile due to the low reduction. We can move this motor quite fast, and we don't have all the weight of lots of gears and bearings on every gear and everything like that. So that is going to be called Quasi-Direct Drive, which is what anything basically that's direct drive but it's under a 10-to-1 reduction is called, and that's how lots of the robot dogs work, that makes them compliant and makes them really agile. But let's have a closer look at this motor. So first of all, they come in a nice metal box, which is rather nice, so we should have a few of those to keep stuff in. And here's the motor itself. Also comes with a sort of ring here for attaching the propeller if you're using it in a drone, and some M3 bolts. And basically we've got M3 bolt holes, I think the M3 on the top and M4 on the bottom for mounting, so it's mounted on these. We've also got this sort of hex nut looking thing on the bottom, which I'll need to mount an encoder on. And then basically the bottom stays still and the top rotates. Like so. So we've then got those M3s there and this centre pin, which we use to attach a pulley on. So it's a 92mm in diameter and 25 wide. So pretty compact, and hopefully we get loads of torque, as I say, because of this massive diameter. So the whole thing is going to be belt drive. I normally use T5 or AT5 belts, and these are polyurethane belts with steel tensioners, and they've got a very square tooth profile, but it's quite shallow. So I've recently come across these belts, which are HTD belts. And this is a 400mm belt, and it's still a 5mm pitch, but the belt tooth is quite a lot bigger there, and these are rubber belts with fiberglass tensioners, and they seem really, really tough. So we're going to probably use these, maybe slightly thinner ones, for this whole build. I also really wanted to talk about the design for openDog version 2. So normally when I build a project, I just suddenly show you the CAD on the screen, spin it all around, show a couple of features, and then we get on and print it, put it all together, and most of the time it pretty much works. But for this build, I really wanted to sort of show how I think about planning the build, the placement of the motors and the belts that we've got here. Obviously we start with some hardware, so we know how big the motor is, and we can get belts in different sizes, but of course there's going to be a spacing, and the pulley can't be so big because it won't fit next to the motor. So I generally start with hardware, but this time I'm going to talk about how I think and the progression of how I design these things in CAD a little bit. So the first thing I've done here is draw out the CAD for the motor, and I'm using Fusion 360 for this whole design. So I couldn't find any CAD to download, so I just basically measured the motor and drew out a fairly crude representation of it. So we've got the right mounting holes in the right place on the back, and that hex nut where the encoder has to mount. And remember, that's the panel that fits down onto something, and the front spins round, and that's where we need to attach the pulley. But basically this is the right diameter, it's roughly the right colour, it's the right thickness, and it's got roughly the right contours on it. The next thing to do is start with one leg and do a rough layout for the motors and the pulleys and see how that mechanism hangs together. So right at the top here we've got the shoulder, and I've just drawn crude blocks here to sort of get that basic layout. So that'll be one motor with a small pulley on it going to a big pulley, and then that will have an axle that goes all the way through, and then this grey block is the upper leg at the moment. I want to keep the motors all mounted up and the mass as high as possible, like MIT Cheetah, so I'm not throwing that mass around when I move the legs. So the knee motor is also up here as well, and that's facing in with a pulley, and then there'll be a belt drive down to the knee, and then the lower leg will be below there, but I just haven't drawn that yet. So that's the rough layout. I've just used blocks, a little bit of extrusion there just to bring this in to get the motor parallel, and we've just sort of done some rough shapes there to kind of work out how it works. So of course this will be the upper leg, which rotates this way, and eventually this blue block will also rotate around this way so that the leg can move in and outwards, and that's going to be an axis that's on this blue block with another motor and pulley in the body of the robot. But of course that knee motor is actually attached on the back and the pulley's facing inward, and the main reason for that is we need to get to that nut there so we can put an encoder on this motor If it were the other way round, with the pulley facing outward, then that encoder would be buried in this leg, and that's got to have something pretty significant attached to this grey thing to run an axle through to the pulley on the other side. Now I can't really do it any other way, because even if these motors and pulleys were on the other side of the blue block, then the two belts would have to cut through each other, so that would be quite inconvenient. So that's really why one motor is on one side with the through axle, and then this motor is here, and it has to be facing that way round so we can get to the encoder. But of course that means the plate it's mounted on moves with the leg, so that whole leg moves together, driven by the motor and pulley on the other side, and then that one then has a pulley that comes down to the knee. So we want to make the leg quite skinny though, so I've got this blue piece here which is actually holding the plate. It's going to hold the other side of the joint, the other side of that axle for the knee, and it's going to hold the back of the motor, and it probably needs some more reinforcement at the top. So that means we're going to have two idlers inside this blue piece which actually stretch that belt down, so it starts small at the top and then it will come down inside, go round some idlers and come out to the knee, and that looks really similar to MIT Cheetah, and that'll keep the belt nice and tight on the top pulley as well. I've now drawn in the bottom of the leg, so you can see that just there, and of course in order to do that we need to be able to have a pulley on here and a belt to go round it, and so we've got this hole here for the belt to go through, and this all needs sorting out so I can actually get the belt in. If I were to make this in one piece, of course it'd be impossible to feed the belt in because it's one round thing with no gaps in it. The one thing I do need to point out is of course this motor at the top for the knee is concentric with the axis for the shoulder, so that means as this leg gets thrown backwards and forwards, even though it's quite long and it'll have some of its own mass, that motor stays on the centre of rotation, so it's not throwing the mass around like it would if the motor was lower down the leg or on the knee, and that'll make things much easier. So now I've started thinking about the third axis of the leg, which is of course that hip mechanism, where we want the leg to rotate around this axis so the leg can move in and out, and of course we have 3 axes and 3 motors in each leg. So that's fine, we've got a pivot point at one end, another pulley, and then there'll be another motor driven off that inside the body of the dog. The only issue we get of course is that if we try and move this around, at some point there isn't clearance and the leg is going to hit that pulley. However, it's probably fine though, because the leg's quite bent at that point. It just means it can't turn inside out, so to crouch down by that amount is probably going to be absolutely fine, and of course rotating it the other way, there's no problems at all, and in fact it can probably do pretty much, well, a 360 less the amount of the degrees of this pulley, so it can pretty much rotate all the way around, which I think is going to be absolutely fine. So if you remember in miniDog version 2, we moved the foot so that it was directly under the hip axis, and that meant that the force drove straight into the axis and we didn't have any weird offsets like we did with version 1. So I've done exactly the same thing with this so that we've got that foot directly under the hip pivot, and that means just bending the lower leg here. So it might look a bit weird, although those are going to face inward, so it won't be too bad, but that does mean that we've got the force driven directly into the pivot point. And here it is with all of its 4 legs on, so I've just done a rough layout here to get a scale for the robot, work out what the footprint is, and basically it's come out a bit bigger than miniDog and a bit smaller than openDog, so somewhere in the middle there. So hopefully it should be light enough for these massively powerful motors, and it should be agile enough. But we really don't know what the belt reduction is going to give us till we build a test leg. So what I've tried to do here is keep these pulleys for the hip motion in the middle, so the motors are in the middle. We could of course put them on the end, but that would make it much longer. So at the moment there's no problem with clearance for the back leg of course to move all the way up, because it's pulleys on the front, but for the front leg we're going to run into that pulley at some point. So it would be better if they were the same mechanism front and back. Then of course we'd have all of this and the motor sticking out the front here, which would cause us quite an offset load. So for now I'm going to keep them in the middle and hope that's okay. We could of course move those pulleys further in and cause a bigger offset on the leg. Then we'd have to do something about getting that foot right in, and at the moment it looks about the right proportions, so I'm going to leave it at that and hope for the best. I've just drawn a placeholder block for the body, and that will be where the motors mount for these hip pulleys, and also of course it will be longer and have electronics mounted on, and something to hold the other end of the pivot points. But that means now in Fusion I can make up the joints so we can move the legs. So now I've got these joints that move the hip joint, and we can see how they'll move sideways, which is really important to see clearance. So first of all, miniDog is not dead, it's staying in one piece. I'm going to keep that as a showcase, and I will probably come back to it in the future and upgrade the servos, but I really want to work on openDog version 2 with the brushless motors, make something much more agile, repeatable and reliable with higher tolerances, and then that's going to really advance my journey of seeing if I can make a robot dog that walks. I'm pretty confident I can now, and if that works really well, we can then apply some of the stuff I've learned in that back to this one to make it work even better and hopefully do all of the other actions like rotating and all of that good stuff. And of course, this is open source already. All the code and CAD is on GitHub. So if you want to try and build one of these, then you can. We've got the statically stable gate as well, remember, as well as the dynamically stable stuff, and all that code is up on GitHub. The next stage for openDog version 2 is that we really need to get the correct motors. I'm pretty sure they're identical to these, but 90 kV. So I've got those on order. And then I need to size the belts and basically size that spacing properly so we can actually do a detailed design, get the pulleys the right spacing, see if we need some idlers, and get the leg the right length so that the pulley down to the knee is in the right place based on what belts we can buy. And then we can go on and make a test leg and see how much force we can convey with probably a 5-to-1 reduction. So that's going to be the next thing. That means I've got to do some stuff, which is going to take more than a week. So basically next week there's probably going to be another project. It may be for 2 weeks, but we'll be coming back to this to do more detailed design. So don't forget to support me on Patreon or through YouTube channel membership if you want to support the channel, or buy a t-shirt, perhaps a miniDog or openDog t-shirt. And of course there'll be one for openDog version 2 once we know what it looks like. Alright, that's all for now.